We are Team Trielectric representing Kungliga Tekniska Högskolan, KTH, Royal Institute of Technology from Stockholm, Sweden. This is our submission to the APS URSI 2016 Student Design Competition. I'm Oskar Björkqvist.
I'm Oskar Dahlberg.
I'm Gustav Silver.
There has been a vast increase of devices that can communicate wirelessly over recent years, and at this moment there are almost 25 billion of them. There is no sign that this trend is decreasing. This has made the ambient radiation levels increase drastically, making RF energy harvesting a viable approach for actually supplying power to electric circuits. This kind of technology can be very useful as it rids the need of batteries and cables to external power supplies, as well as limits the need of maintenance on these circuits, as they would be completely self-sufficient. To test this hypothesis, we considered a smart building application using KTH campus as our testbed. In situations of smart building sensors, RF energy harvesting is very suitable considering that the building is likely situated in an environment rich with ambient radiation. In this picture, we have multiple sensors being used in an environment where we have both cellular and Wi-Fi signals available. To further qualify the available RF signals in a building environment, we need to consider different scenarios.
Electromagnetic fields depend heavily on location, and it is therefore necessary to assess what kind of radiation that is available in different kinds of environments. To do this, we made some measurements of the ambient radiation levels around the KTH campus. We then wanted to measure the power levels in these signals. To do this, we constructed two monopole antennas. When measuring, we used the whole peak functional spectrum analyzer and obtained the following results. As we can see, the highest measured level was minus 20 dBm.
In order to convert this energy into useful DC power, a rectenna is utilized. The rectenna consists of, first, the antenna that acts as an interface between the RF signals and the rectifier. The rectifier stands for the RF to DC conversion. A charge pump is used if the output voltage needs to be increased. At last, either a supercapacitor is used for storage, or the rectenna is connected directly to the sensor, which is the load. The RF harvesting system is designed to be operable in both 1.7 to 2.1 and 2.4 to 2.5 GHz bands. In the scenarios considered, there are cases where either the cellular or the Wi-Fi system is redundant, and thus a modular approach is adopted to design the system such that they can work either standalone or jointly. RF harvesting systems often use omnidirectional antennas, but this results in a low gain, and the system relies highly on available input power. Our system uses directional antennas spatially placed to get full azimuthal coverage. We have also extended the full wave rectification to a MISO perspective. By employing two antennas receiving in the same polarization and a voltage doubler in each antenna, we can use both positive and negative rectification, resulting in a differential voltage output.
We have utilized all the phases of the cuboid with broadside and endfire antennas for full azimuthal coverage. For the Wi-Fi antenna, an X.load dual polarized patch antenna was used. The slot loading yields size miniaturization by 10%, with gain above 9 decibels and efficiency of 98%. Placing two patch antennas in each of the four surrounding phases and combining the same polarization ports in each phase with a MISO rectification approach, we can obtain almost 500 mV output voltage in a rich scattering and polarization diverse environment, such as a conference room.
In the two remaining phases of the cuboid, we have placed linear tapered slot antennas
that radiate in the unfired direction for azimuthal coverage. A corrugation pattern is placed along the edges to suppress the radiation from these. The antennas have about 4 dB gain, and the two antennas looking in the same direction employ again the MISO rectification approach. From the LTSA, we can obtain 320 mV in the best case. For the corresponding bands, we have developed one dual band rectifier for the cellular band and one single band for Wi-Fi. We have constructed all the circuitry using our in-house facilities. Here we can see the system in closed form and the two modules. Also, we present a partial view of the system with only two MISO rectifiers connected. Here is an illustration of measurements of voltage and current performed in the lab when we used two signal generators to send in the cellular and Wi-Fi bands and received with our RF harvesting system, together with a table with the system measurements in our defined scenarios for smart building applications.
This was our submission to the contest. In this project, we have learned that RF energy harvesting can be very useful, and we expect to see more of it in the future. We are Team Trielectric from KTH, and thank you for watching.